If you've ever listened to music and had someone approach you to have a quick conversation, you may have kept your headphones over one ear. For most people, it'll free up their right ear for the conversation. But this isn't just because your dominant hand is on the same side. Believe it or not, we have two brains. We don't notice this because those two brains are in constant communication, exchanging and confirming information with one another like a single coordinated entity. But they each have a unique task and method for processing information. Brain lateralization, or the isolation of specific mental tasks to different hemispheres of the brain, plays an essential role in vertebrate biology. It allows for increased reflexes, efficiency, and the ability to multitask. In other words, it's just the best evolutionary design. The information processed in each hemisphere is shared between themselves via a neural highway called the corpus callosum. However, this highway is not always available. A rare birth defect known as agnesis of the corpus callosum prevents the fusion of the corpus callosum neurons. Therefore, information from the two hemispheres is unable to be shared with one another. This creates what's called split brain personality, and the brain can no longer share its different processing outputs. The corpus callosum highway can also be severed via surgery as an extreme treatment for specific types of epilepsy. Those who have undergone such a surgery exhibit some of the most fascinating phenomena in psychology. Our brains control our bodies through what is called contralateral control. That means all motor functions and perception from the right side of the body are processed by the left brain, and those from the left are processed by the right. When our two brains cannot communicate with one another, then each side of the body is controlled independently from the other. Because we have two brains, each processing information in different manners, giving each one the same information yields different results. The left hemisphere is more logical and sequential with its processing of information. This is also where the language center for most people is. The right hemisphere is conceptual and contextual with its processing. This is where we discover subtext and connect different concepts through intuition and imagination. Let's go through an example to understand what that means. Consider the phrase, "I never said she took my money." There are multiple different ways of presenting this sentence depending on which words are emphasized. The left brain is sequential and logical. For each instance, it simply considers the literal sequential meaning of those words in that order. Whereas the right brain processes the context, the tone, and the rhythm of the sentence. This is called prosody. If we consider this version, "I never said she took my money," our right brain recognizes the emphasis on my and understands there's an underlying subtext to the sentence than just the literal meaning. When we combine the processing output from both halves, we extract more information than with just a single brain. That being, the woman subject of the sentence must have taken someone else's money, and there was a misunderstanding when the speaker told them about it prior. This is the advantage of processing and sharing the same information in two different manners. We get more out of it. Split brain patients are notorious for knowing something without consciously being aware of this. There are many videos that go into depth on that phenomenon. Personally, the most fascinating drawback for split brain patients is that their brains can no longer compare their processing outputs. I've linked a video of many of the experiments and crazy things a split personality patient can accomplish in the description. I highly recommend watching that after this video. I want to share my favorite experiment that demonstrates the different ways information is processed between our two brains. 16th century painter Giuseppe Arcimboldo painted human portraits out of still life. To us, it's clear the human form is the main feature of these paintings. But what happens when you show the same paintings to each hemisphere? When showed to his left brain, the split brain patient's brain saw the literal makeup of the image and pointed to fruits being the main feature. However, when shown to the right hemisphere, the brain focused on the context of the shapes, the features, and the shading. The right hemisphere recognizes them as a human profile, and thus the patient selects the human as the main feature in the image. This highlights the importance of lateralization and communication of our two brains. It's starting to look like lateralization may play a significant role in autism. Those with autism are notorious for either struggling with language and/or interpreting social cues. These are two fundamental functions of the left and right brain, and with less lateralization, it may be more difficult for these functions to develop and specialize. One of the best methods to analyze and observe lateralization is with dominance. As mentioned in the last video, lateralization naturally leads to a dominant side. For most people, our right side is dominant, but for about 10%, they exhibit non-right dominance, meaning they're left-handed or ambidextrous. Although we say language is processed in the left brain, a study of handedness and language processing found a linear relationship between the two. For strong left-hand dominant individuals, over a quarter of them have language processing dominance in the right brain, proving left-handed people are freaks. I'm joking, but this shows the relationship between handedness and lateralization. The autistic community, however, has a much larger non-right dominant population. Roughly 60% of individuals are non-right dominant. This percentage also correlates with language difficulties, meaning autistic children who struggle with language have a higher rate of non-right-handedness. I want to stress, however, that this is still early theory. A meta-analysis of experiments describing lateralization in autistic minds found it very difficult to combine the results into a concrete conclusion. Very few experiments actually specifically studied lateralization. Those that did directly study lateralization all had different methodologies and manners for measuring it. Some saw significant changes in lateralization and others saw very little. But the analysis does suggest that there is a trend for decrease in language lateralization, with no research specifically looking at right brain lateralization. It is believed that autistic brains have an overconnectivity for neighboring neurons and an underconnectivity for distant neurons. The corpus callosum of autistic individuals is consistently smaller than control brains, meaning signals are not efficiently shared between hemispheres. This is also reflected in individuals with agnesis of the corpus callosum who demonstrate autistic traits such as language and social difficulties. Additionally, normal corpus callosums are anisotropic, meaning it doesn't send signals with equal ease in both directions. Normally, signals arrive a little over 3 milliseconds faster when traveling from right to left. Autistic corpus callosums have a lower anisotropy, meaning it's more balanced with sending signals in either direction. All of this is to highlight the advantages of having two unique brains which can efficiently share their processing outputs with the other. Our two brains also play a strong role in emotional processing. It used to be believed that our emotions were processed solely in the right side of our brain, as patients with lesions and damage to their right hemisphere often showed emotionless responses to distressing or negative news. However, now we believe that emotions are processed on both sides of the brain in what we call emotional valence. How we feel is determined by the relative activity in a certain region. The left side of the brain processes positive emotions, and the right side processes negative emotions. By administering anesthesia to the right hemisphere, patients reported a sense of euphoria and contentness, whereas administering anesthesia to the left hemisphere elicited a sense of negativity and distress. We can also infamously see this result in how dogs wag their tails. When they are happy and excited, more of their left hemisphere is active, which causes their tail to prefer to wag to the right. Whereas when dogs are threatened or upset, their right hemisphere is active and thus their tails wag to the left. Measuring dogs' cardiac activity and stress also indicated they can recognize this wag behavior in other dogs, reacting negatively to dogs wagging their tails to the left. Lastly, how can we use our knowledge of our brains to our benefit? In the introduction, we wondered why we prefer to listen to music in the left ear and listen to people talk in the right ear. Hopefully, you're realizing this is because of the different ways our brains process information. And due to contralateral control, information from one ear is shared with the brain on the other side first. This means our right ear is better for processing and listening to sequential and logical information like pure language. Conveniently, this is also the ear right-handers hold the phone to. The left ear is better for tonal and rhythmic processing like that in music. But if you're strongly left-handed, there's a possibility this is reversed for you, and your left ear is better for listening to language. So if someone continues listening to music while you talk to them, understand there's two brains at work and they're fully capable of listening to you, if they want to.